For over 50 years, every day in every aspect of our lives, we've relied on polymers derived from oil. Yet only 4% of oil usage goes into polymer production. But what's the common image the public has of plastics? An environmental nightmare? It would be if plastics were allowed to pile up over the years, turning our planet into a giant rubbish dump. But is this what's really happening? No. Plastics can be and are being recycled.
Recycling of plastics is not a new idea, but a very successful idea which has been done for more than 20 years in Europe. In Europe, on the whole, there is no legislation affecting the recycling of plastics. But in Germany, for example, we already have a legislation on packaging, and we are certain that our government and the other governments of Europe are actively working to introduce legislation on recycling of all materials.
Plastics in general make up only 7% by weight of solid municipal waste in Western Europe, and polyurethanes make up less than 5% of this mixed plastics waste. Although it's a very small percentage, the industry is taking it very seriously. So research into recycling is going on in all sectors of the polyurethane industry to improve the processes available and to find new markets for recycled products. The major industries using polyurethanes are furniture, bedding, automotive, construction, and domestic appliances. One of their main advantages is that they last a very long time. In furniture and cars, they last 10 years or more, and in building materials, they can last over 50 years. This means they produce less waste than other materials because they're not replaced nearly so often. But eventually they will join the waste stream along with production waste.
Polyurethanes are an extremely versatile range of polymers prepared from the reaction of polyols and isocyanates.
Polyurethanes are so-called tailor-made polymers. They are tailor-made for each individual application.
The production process, which takes place at the customer, is tailor-made for each of the various applications.
Tailor-made polyurethane raw materials as well as tailor-made processing technologies imply that the recycling of polyurethanes has to follow tailor-made recycling routes as well. Polyurethane waste is arising during production. This is the most easiest case for recycling because the cut-offs, the trims, they are usually very clean material, easy to collect, easy to treat. Opposed to that, polyurethanes after use are very difficult to retrieve. Normally, there is no infrastructure in place to do so. Very often, they will be commingled with different materials. They may be dirty and contaminated.
Public opinion, economics, and environmental responsibility demand recycling wherever possible. But all factors must be taken into account before any particular method of recycling can be considered viable. Transportation and dismantling a product to retrieve the polyurethane for recycling might be so expensive and use so much energy that it would be better to incinerate the waste locally and recover its energy content. At the moment, most mixed plastic waste, about 70%, is still treated by landfilling. In the case of polyurethanes, it's not likely to harm the environment, but it's becoming expensive because it uses valuable space. It also causes raw materials and the energy they contain to be lost. Polyurethanes are used to make flexible foam, rigid foam, integral skin semi-flexible foam, and reaction injection molding, RIM. Recycling these products is becoming more and more successful and falls into three main categories: mechanical recycling, chemical recycling, and recovery of the energy content of the polymer. Rebonding is the most widely used recycling process and has been successful for more than 30 years. It's a mechanical process and can use 90% waste polyurethane mixed with 10% binder in the new product. Here, flexible foam from production scrap is being rebonded into recycled flexible foam. The waste is shredded and then granulated and mixed with binder. Dye can be added to give the recycled foam a more uniform colour. The mixture is then compressed. Steam, pumped into the moulds, activates and reacts with the binder. The recycled foam can be used in a wide variety of products, such as furniture, cars, sports mats and carpet underlay. Manufacturers are keen to show designers that polyurethanes are being recycled and have many advantages over other materials.
The public's opinion on recycling of plastics, unfortunately, is that during the process of recycling, properties are being downgraded. It does not include possibilities or applications where additional new properties are being created through recycling. As far as polyurethane is concerned, we are able to achieve a higher density and higher hardness with recycled polyurethane or rebond foam.
One use of rebond foam is in sports mats, where a high level of protection is required.
With rebond foam or recycled chip foam, you can achieve very high density foam, which, for example, is not possible with virgin polyurethane slabstock or flexible foam. And this high density you require to achieve the protection you want when you jump or fight on a mat.
The rebonding technique can also be used with both flexible and rigid foam from production waste or post-consumer waste. The waste is recycled here into a variety of pressed boards. The shredded waste, mixed with a binder such as polymeric MDI, is subjected to a high pressure and a high temperature to mould the recyclate. Rigid and flexible foam can be used mixed together to make thick boards with a very smooth surface finish. Thinner boards need to have textiles and natural fibres added to make them stronger. Low-density boards are used for thermal insulation in the walls and floors of buildings. Higher densities are suitable for furniture and kitchen and bathroom units.
These boards are much better than the usual boards. They have a high stiffness, high strength and improved water resistance. The market's expanding. The boards are improved in relationship to plywood, in water resistance, sound insulation and thermal insulation. The price is not much more than normal plywood, and it depends on the grade of the equipment and the yield of the equipment. It's a question of investment.
Polyurethanes can be ground into fine powder, added to the original polyol mix as a filler and recycled into the production stream. but this is only viable with pure waste polyurethane being recycled into the same type of polyol stream. This is a pilot operation for making rim regrind filler. A similar process can be used with flexible and rigid foams. Shredding the waste and then grinding it to a uniform powder is a vital part of this process. Different grinding processes are required for flexible and rigid foams and rim. An impact disc mill is used here on rim waste. Rim often contains glass filler and amines in the polyol mix. When regrind filler is added to the polyol, it can cause disturbances in the mixture, giving the recycled product surface problems and other undesirable qualities. This problem has been overcome by using 3 separate component streams going to the mixing head. The first carries amine and polyol with glass filler. The second carries amine-free polyol and rim regrind filler. The third carries the diisocyanate. When the components are mixed together, there's a rapid reaction and high-quality rim is produced.
This three-stream technology enables us to recycle painted rim parts without removal of paint back into the same application while still meeting car manufacturers' specifications. Most of rim is used in the USA, and there this technology is already being practiced on production scale.
Rim is used for highly visible exterior parts of cars, such as bumpers and body panels, and the recycled product must meet the highest specifications. Finely ground rim can also be compression molded at about 180 degrees Celsius and pressures of more than 350 atmospheres with very good results. This process allows 100% recycled rim to be used. Like other recyclates, compression molded parts have certain improved properties compared with virgin rim. Also, their good flowability in compression molding allows the production of complex shapes and flat parts of high quality. With most recycling processes, there is a limit to the percentage of recycled material that can be added to the new product before it changes its appearance and physical characteristics. There's also a limit to the number of times any product can be mechanically recycled, because the molecules change and the product gradually degenerates. Glycolysis, a form of chemical recycling, is one commercially available solution to this problem. This company makes elastomeric foams for vibration damping materials and uses glycolysis in the recycling of production waste. They produce mats of varying densities and thicknesses. They're used under the beds of railways and under individual rails for trains and trams. They're also used to dampen vibrations in buildings and in machinery. Much of the foam produced here is made from 35% recycled polyurethanes, and it's vital that the recycled product is predictable and meets rigorous specifications. This is one of the first glycolysis units to operate at a commercial level, and other companies are now making similar investment in this process. During glycolysis, the polyurethane chains are split by the action of glycols into residual species and polyol. This then becomes the raw material for the synthesis of new polyurethanes. Waste is collected and shredded and then stored in a silo. Waste, polyol, glycols and a deamination agent are then mixed together. The glycolysate, or recycled polyol, is then pumped to join the diisocyanate stream on the same production line, so forming a closed-loop system. It's important to keep pure waste streams separate because every waste stream needs different glycolysis treatment. Although all polyurethanes can be glycolysed, they can't all be recycled in closed-loop systems at present, and so the use of glycolysis is restricted. Another chemical process for recycling polyurethanes is feedstock recovery. Although still at the pilot plant stage, results are encouraging, and it will soon be operating at a commercial level in several plants. A feedstock recovery plant should ideally be located within a general petrochemical plant, so that recovered feedstock can be mixed with the plant's normal petroleum feedstock. This pilot plant is recycling granulated mixed plastic waste from packaging. It could also operate with a small percentage of polyurethanes in this waste. A high concentration of polyurethanes would require modifications to the plant, and other methods are better for recycling such waste at present.
In the BASF Feedstock Recovery plant, we are cracking down polyolefins from packaging plastics to basic petrochemical products. Feedstock recovery of plastics waste means high temperature treatment to break down the molecules to raw materials, which goes back into the chemical feedstock, where they can be used for building up new chemicals.
During feedstock recovery, potentially corrosive materials are removed. Of the remaining fractions, 15% comes out as gas, 60% as oils, such as naphtha, 20% as wax with high molecular weight hydrocarbons used as feedstock for acetylene and synthesis gas, and 4 to 5% forms a residue from non-plastic materials. The recovered gas and oil are broken down in the steam cracker into ethylene, propylene and an aromatic fraction. These are then used in the production of new polymers. Polyurethanes can't be recycled indefinitely. But whether from production waste or post-consumer waste, they have a recoverable energy value equivalent to that of coal. They're fossil fuels in another form. Incineration is the only process available at present for large quantities of waste if landfill is to be avoided. Incineration allows the energy to be recovered from organic materials and inorganic materials to be recovered and treated as required. And although the public is concerned about pollution from incineration processes, polyurethanes actually produce fewer harmful emissions than coal when they're incinerated. Modern waste incineration plants meet very high standards for control of emissions and meet stringent safety requirements, so causing no threat to our health or environment. Conservation of all raw material resources will become even more important in the future than it is today. This will increase the appeal of recycling to the manufacturers, designers, and the public. Recycled polyurethane should be regarded as a new class of materials, able to meet the requirements of new and emerging markets.
Very often, recycled polyurethanes have different properties. They have, for instance, higher densities or higher load-bearing characteristics. By this, they are far more suited for the different application to fulfill than virgin material.
For the sake of our environment, we must avoid unnecessary waste. we must insist on environmental product design. And we must continue the search for new markets for recycled polyurethanes. We can have confidence that the industry is handling waste in an economically and environmentally responsible way. Investment in suitable infrastructures will enable us to have the opportunity to exercise the best option for recycling. Polyurethane recycling is here today, and more recycling will be here tomorrow. The technologies for recycling polyurethanes exist.